Greetings, Panthers. Dr. Augustine today. Today we're going to talk about electrolyte versus non-electrolyte solutions. This is going to cover chapter 5.4 intro, types of aqueous solutions and solubilities. Actually, we're not talking about solubility, just types of aqueous solutions. Major topics: difference between an electrolyte and a non-electrolyte solution. What causes a solid to dissolve into a solution? Why does a solid dissolve at all? Why are some solutions non-electrolytes? And the terminology of strong versus weak electrolytes. So first of all, let's start out with the question of what causes a solid to even dissolve into a solution. So if we drop a chunk of material into a solvent, and we'll just take water as our solvent, and suppose this thing that we've dropped in is sodium chloride. It could be sugar, could be anything that we've dropped to dissolve into the water. If you think about it, there's got to be something that's holding this stuff together to begin with, the sodium chloride or the sugar or whatever the material is that we've placed into the water. So there's some forces that are holding this together. And the forces that are holding it together are called intermolecular forces. We're going to deal with this much more later on in the semester. But basically, if you want to think about what those forces are, they're either positive or negative charges. In physics world, positives attract to negatives. They exhibit an electrostatic interaction or Coulombic attraction to one another. So of course, in the case of sodium chloride, it's fairly easy to see what might be holding it together. Remember, the sodium atoms are actually not atoms, they're actually ions. So it's actually a sodium plus one and a chlorine minus one. So the positive and negative charges are going to get attracted to each other. Sugar, on the other hand, is a molecular compound. It's not made up of ions. And that interacts with the water because the water has a shape to it and the water has a sort of partial charge. So I'm going to introduce a water molecule that has a bent geometry. You'll learn about this more later on in the semester. But there's like a partial negative charge on the oxygen side of the molecule and the partial positive charge, and we use a little delta symbol to indicate the partial. We have a partial negative side on the oxygen side of the molecule, partial positive on the hydrogen side of the molecule, and those things interact with the groups, the atom groups that are around sugar and the atom groups that are around sodium chloride. Now I'm going to show you a sugar molecule in a minute, but let's deal with sodium chloride first. That's kind of the easiest one to understand. So if we have an ionic compound like this, we understand what holds the solid itself together, and that is this Coulombic attraction, also known as electrostatic interactions. So this picture right here shows the sodium and chlorides, the sodium ions and the chloride ions attracted to one another. Sodiums are the purple ones, the chlorides are the greens. So a piece of table salt that we drop into the water is held together with electrostatic interactions, and that's what basically the glue that's holding this together. But because water is polar, because water has this partial negative side to it and partial positive side, remember the hydrogens are the positive side and the oxygen is the negative side, what happens is the water molecules are able to extract these ions. Okay, so that means the interaction between the water molecules is stronger or able to overcome the interactions between the ions in the solid. Now, it's a little more complicated than that. It has to do also with the degree of disorder, which we will learn about in the second semester. But for now, let's just say that force is strong enough to pluck these ions away from each other and to then separate them. So your picture, if you're to look at things on the molecular scale, your picture should be positive ions surrounded by waters, that's called hydrated, and in this case with the oxygen sides pointing towards the positive ones, and negative ions, that's the chloride ions, surrounded by water molecules also, with the hydrogen side of the molecule surrounding the ions. And once this dissolves, these are all separate from one another. They're not together. So I want to make a really important point. If you write something like this, NaCl aqueous, what that is really implying on the molecular scale is you really have Na plus ions, aqueous, plus Cl minus ions, aqueous. In other words, when you determine that an ionic compound is aqueous, what that has really done is it's actually broken up into its ions. Sodium ions and chloride ions. So this is the picture you should have. You should have the ions surrounded by water and not attached to one another. Okay, this picture right here is before they dissolve. This picture right here is after they dissolve. So when you write a structure out like this, sodium chloride aqueous, that AQ is actually implying that you've actually broke this up into ions, and these are actually floating around separate from one another in solution. Okay, so let's take a look at sugar. So sugar is C12H22O11. That's sucrose, common table sugar. Now you notice that's a molecular compound. It's not an ionic compound. And here's a picture of a sugar molecule. And because it's not an ionic molecule, it does dissolve. Okay, so you could put an aqueous next to this. You could say we have a sugar solution, but that is not going to break up into ions because there are no ions to be broken up into. But there are groups, hydroxide groups, OH groups on the end of the molecule. So the molecule is actually made up of these functional groups, and this is beyond the state of what we want to talk about right here, but just quickly mention there are functional groups on the edge, on the outside of this sugar molecule. There's carboxylic acids, there's OHs, and these can also interact with the water molecules through what's called hydrogen bonding. This is something we'll talk about later on in the semester, but it's the same electrostatic interaction, but it's not quite as strong as the ionic interaction. And because of hydrogen bonding with the water molecules, they are able to also pluck away individual sugar molecules from one another. So when it starts out as a solid and then they end up getting broken apart by the water molecules and dissolving. Okay? So I want you to picture two different types of species. We have ionic species and we have molecular species. Ionic species break up into charged ions, and molecular species break up into the molecules surrounded by water, but not charged. Okay, so that's an important distinction. So if you have sugar, it's a molecular species. The water molecule is able to interact with it through hydrogen bonding. They're able to separate away from each other, so they are actually separate molecules in solution, all surrounded by waters. But there's no charged species in it, okay? There's no ions in it. Ionic compounds break up into charged ions, which are also surrounded by water. And we call this hydrated. Okay, the water molecules are surrounding these ions and hydrating them. So that leads to two different properties of solutions depending on what these are. So if we were to take a battery with some electrodes hooked up to a light bulb, and we had some water, and when the electrodes were dropped in the water, and we poured table salt, NaCl, into the water, we would see that the light bulb would start glowing. However, if we took sugar and dissolved it in the water, it would not start glowing. So the glowing light means that the water is actually conducting electricity, but the not glowing light means it does not conduct electricity. So I know your parents or your mom has told you, do not take a shower with a heater or with a hairdryer or something like that because you can get electrocuted. The reason is not because of water. So pure water really does not conduct electricity. It's an insulator. It's the ions that are dissolved in the water that conduct electricity. Now the reason why you shouldn't be doing this in your bathtub is because there are ions dissolved in city water because the water is flowing over minerals and gradually dissolving ions. So there are chloride ions and magnesium ions and iron ions and sodium ions all dissolved in the water that you drink when you pour it out of the tap. If your home was made had a massive deionized water system and that's what your shower was and you spent $1 million on that, well, the water wouldn't really conduct electricity. But in any kind of normal water system, there are dissolved ions in the water. That's what causes the conduction of electricity. It's not the water itself, it's the ions. Remember, the conduction of electricity requires the flow of charge from one electrode to another. So because ionic compounds are charged species, that enables the flow of ions. So that leads to a new name. And if we have a material or a aqueous solution that conducts electricity, we call that an electrolyte solution. So an electrolyte solution conducts electricity, which must mean that there are ionic compounds dissolved in the water. And if it does not conduct electricity, we call that a non-electrolyte solution. And this is going to be molecular compounds, like sugar, like alcohol. So ethanol is CH2, CH3, OH. If you take an alcohol solution and dissolve it in water, it will not conduct electricity. The light bulb would not turn on, it would not conduct electricity. Ionic compounds, any ionic compound that dissolves, anything that you can write an AQ next to it, aqueous, that is going to conduct electricity. That's known as an electrolyte solution. Because this is chemistry and life isn't always nice and easy, we need one more subtle detail. So I've already told you about non-electrolytes, and we already said this is something like a molecular species that would be dissolved in water, something like sugar, something like alcohol. If we stick this in water, it will not conduct electricity with a battery. Under the electrolyte umbrella, we have two different cases. Okay, so an electrolyte actually can be considered a strong electrolyte or a weak electrolyte. What do we mean by strong electrolyte and weak electrolyte? A strong electrolyte is caused by a material that's dissolved by a solute which completely dissociates when dissolved in water. So if we have some solute that dissolves in water and it completely dissociates, like sodium chloride solid, if we put that in water, will completely dissociate into Na plus ions and Cl minus ions. If we have a case where it completely dissociates, we call that a strong electrolyte. One of the implications of this is if we have a solution that has a certain concentration. So for example, pretend we have something like calcium fluoride, CaF2, aqueous. We know that this dissociates into Ca2 plus ions plus 2F minus ions. This is a strong electrolyte, completely dissolves. So if we have something like calcium fluoride, which completely dissolves, one thing we got to be a little bit careful of when we're talking about stoichiometry is if this was a 0.1 molar solution of calcium fluoride, the molar concentrations of the calcium ions and the fluoride ions would not be the same. In fact, we'd need to do a little bit of stoichiometry if we wanted to find the calcium ion concentration. And I'm going to use a new notation for you. If I use a square bracket, that means molar concentration. So if I had 0.10 moles of CaF2 for every 1 liter of solution, I would need to multiply this times 1 mole Ca2 plus for every 1 mole CaF2. All right, so that is obviously equal to the same concentration solution. So this would be a 0.1 molar solution of calcium ions. Again, these square brackets mean molar concentration. So the concentration of calcium ions would be 0.1 molar. That's not surprising. The concentration of fluoride ions, however, would be equal to 0.1 moles CaF2 for every 1 liter of solution times 2 moles F minus for every 1 mole CaF2. Okay, that's going to cancel that. I should have canceled this up here. So I'm going to be left with 0.20 molar fluoride ion concentration. All right, so strong electrolyte means whatever this concentration is here, it will completely dissociate, and whatever the concentrations are based on stoichiometry, I'll have the same molarities or the expected molarities, assuming it completely dissociates. Okay, that's a strong electrolyte. Completely breaks up into its ions. There are no ions together. That's what this picture is trying to show. Sodium chloride is completely dissociated into the sodium ions and chloride ions, and the light glows very bright because it's a strong electrolyte. A weak electrolyte is something that only partially dissociates. So let me give you an example of this. HF is an example of a weak electrolyte. So if I have an aqueous solution of HF, it does not completely dissociate, only partially dissociates. And the way we illustrate that is with a forward and a reverse arrow. This is what's called an equilibrium situation. And we would get H plus ions, and we would also get F- ions. And if this concentration was 0.1 molar HF, these would not be 0.1 molar here. They'd be quite a bit less. We're not going to go into the detail of figuring out what that quite a bit less is. That's a great long subject of Gen Chem 2. Because this is an equilibrium process, we can calculate what these concentrations are going to be, but they're not going to be obvious. And that, again, that's a subject of general chemistry too. So if you see an ionic compound with one of these double arrows, that is going to be a weak electrolyte. And it's not always obvious which one's which. You may have to have a little bit more information to know which one's a weak electrolyte and which one's a strong electrolyte. The effect this is going to have is some of these are going to be dissociated and some of these are not. This is an HF, this is acetic acid, vinegar, but it's showing the same thing. Sometimes they're together, sometimes they're not, sometimes they're separate ions, sometimes they're not. It partially dissociates. They are in equilibrium. It would be called a weak electrolyte, and then you can see that the light glowing, these are the same concentration solutions. The light glowing is much dimmer because this is a weak electrolyte. That wraps up non-electrolytes and electrolytes, as well as strong and weak electrolytes. And so I thank you for watching, and tune in for more videos. Thanks.